session today, we're mostly going to show you guys how to get set up with the GitHub repo that contains some Jupyter notebooks that you can explore and play around with a little bit to get a feel for what you're going to do with the planet hunting challenge. And then you're just going to have some unstructured time, hopefully at the end, to get to work on the planet hunting challenge while we're all here to support you. So let me share my screen. Okay. So the first thing we need to do is go find that GitHub repo that contains the Jupyter notebooks. So let's go to the agenda, the Sagan Summer Workshop page. And then if you scroll down,
do you want to maybe just expand your screen a little bit? It's quite small for me.
Thanks for letting me know.
No problem.
Okay. Now, yeah, okay, so if you click agenda, and then at the top, there's hands-on session information. Okay, it's a little bit hidden, but there's one way to get to it here, relevant materials, and that'll take you to GitHub. I believe also if you just search on GitHub for Sagan 2020, you should be able to find the same place too. Once you get here, you can use Git to download these if you guys know how to use that. Otherwise, I'm just going to show you how to download it as a zip package. So if you click on this code button here, it gives you a drop down and you can say download zip. That will save it to wherever your default download is, download directory for your browser is. Okay, and so mine automatically expanded.
A lot bigger. It's super tiny on my screen.
Yeah, which ones are tiny? Just the terminal?
Web page.
The web pages too? Okay.
Whatever you're working on, if you could just make it much bigger.
Okay. Okay. How's the terminal? Readable?
Yeah.
That's better for me anyway. Although bright green on black background is a little hard to. Okay.
Is that hard? Oh, okay.
Yeah, just don't.
Okay, so I downloaded the zip package. It automatically expanded it. So now I have this folder here, Sagan 2020. So I'm going to change into that. Then there is a tutorials. Inside there, there's several of them. And we're going to go to the RV one first. Okay, so once I'm in here, there should only be this one file. And I'm going to launch Jupyter Notebook from here. On your machine, most likely, this will automatically pop up with a browser window. On mine, it's set up a little differently. So I have to actually go to the site. And so you should see something like this as soon as you launch that Jupyter Notebook command. And then we click on the IPython notebook for the rate of velocity measurement. I hope that you don't see this error. Okay. Okay, so I'm just going to go through this rather quickly. I'm not going to explain everything that's going on in this notebook. It's more for you to read and play around with, but I just wanted to go through it to show you how notebooks work in general and some of the basics of what we're doing with this cross correlation. And Heather's going to help explain some of the details as well. Okay, so again, I'm not going to read all this stuff. That's for you. So up here, we're just doing some basic imports for Python and defining some things that we need, like the speed of light. Another thing I'm doing here is testing that this works on my machine. So hopefully it works all the way through. Okay, so here we're defining some functions that we're going to need later. So the details aren't super important, but there's two functions. One is to convert wavelength to delta velocity. This will help to shift our template spectrum or our mask against the velocity or the observed spectrum. as a function, and then we can plot it as a function of velocity. Log lambda just resamples our spectrum, which is going to be defined as flux as a function of wavelength. This converts our wavelength scale to a log wavelength scale, and this is necessary to do the cross correlation. Okay, so we defined our functions there. Now in this package, I've given you a set of synthetic spectra that are all shifted to different velocities. So this all I'm simply loading up those spectra and appending them to a list. And then we're just going to plot what one of the spectra looks like, okay? So each one of these, so I'm just picking out the first of that list. I'm going to plot the wavelength versus flux. So each of these have columns, and the ones that you really need to worry about are these wavelength and flux. So if you pull out any of these elements from that list, you should have columns that have wavelength and flux, and you can plot those or analyze those. Okay, so that's just plotting the first spectrum. And now I'm going to plot two of the spectra on top of each other and zoom in a little bit. And you'll see that they're shifted, right? The red spectrum is shifted a bit relative to the black spectrum. Now this shift is exaggerated a lot compared to the kind of shifts that you might expect to see for exoplanets. But remember what Jason said, you do actually see large shifts in your observations, and that's mostly just due to Earth's orbit around the sun and rotation as well. So this is not that unrealistic relative to what you would see in real data. Just that the majority of this shift that you're going to measure here is just Earth shift rather than the planet shift. Okay. And so now we're going to go through the cross correlation, the details of this. So I wanted Heather to describe what's going on here, if she's on. Okay, so first we're just going to do a little preparation here and convert our wavelength to log lambda scale. And then we're going to build a reference essentially. And then this is really where the cross correlation work happens. So do you want to talk about your comments here, Heather?
Yeah, no problem. So think of this reference as that sort of mask that Sharon was talking about earlier today. And you do have a nice image from Sharon's talk just hiding behind your notebook. If you want to just pull that up and kind of make it so that we remember that basically what we're trying to do here is that we have two different spectra or two different things, two different vectors that we're interested in, and we want to know the relative shift to one another. So we're basically just sliding them along one another, trying to find when we get them to match up. You can think of it sort of as like a sliding dot product, because what we're interested in is the cosine of the angle between these two vectors. So what's done at the very top bit of this sort of input of 164 is we define a leg grid. So you can look at the function there, but essentially what we just want to have a grid that we're going to be cross-correlating along. And so one thing that's important for the technique that we're showing you here today is that the spacing is even. You don't always have to have that to perform a cross-correlation, but in this case you do. And it's also nice to normalize your series. So again, it's not strictly necessary in all cases, but there can be an amplitude dependence with your series. So normalizing it is sort of a best practices, I would say. And when you're looking at what the functional form is for a cross correlation, it looks quite similar to a fast Fourier transform. And so that's the main tool that we're going to use here in a few useful theorems. So this is all kind of commented out. So I'm hoping that you can take a look at this in your own time and dive into it. But the advantage of this fast Fourier transform is it's really going to help out computational speed. But it's nice to look at the guts of it. So I tried when writing this out to show you the various sort of Python like NumPy or SciPy functions you can use to do various things, but also try to step you through kind of from the ground up. So normally you would want to zero pad, and so that means you're just going to add a bunch of zeros on either side of your array, and that's because when we're shifting these things, we want to make sure we don't shift off the end, because we're doing there's a circular component to what we're looking at. It's circular cross correlation when we're doing the fast Fourier transform. So we go ahead and we normalize, and then we compute the fast Fourier transform of each one. So you'll notice that in here it's just referring to A and B. That's just because the reference and the original one have been renamed, but it's just a nuance. It was just a way to preserve the reference flux and the original flux so that you didn't accidentally overwrite them. But I would encourage you to add your own bits to these and to go ahead and plot along at each step so you can see what they look like. So we compute the fast Fourier transform, and then we want to get the complex conjugate. And the reason for that is because you have the convolution theorem that says the Fourier transform of the convolution is the product of the two Fourier transforms. And then you also have the correlation theorem that says multiplying the Fourier transform of one function by the complex conjugate of the Fourier transform of the other gives you the Fourier transform of the correlation. So that's kind of a mouthful. So I would really encourage you to read the text and go back to your sort of physics 101 and remember these theorems. So this is essentially what we're doing. We've taken the fast Fourier transform of both. We take the complex conjugate of one, then we multiply it by the Fourier transform of the other. And then we want to take the inverse Fourier transform, because one of the beauties of the Fourier transform is it puts us into the frequency space where things are nice. But of course, we're interested in getting back into the sort of time domain, or in this case, the radial velocity domain. So we take the inverse, and then because the fast Fourier transform does a cyclic or circular cross correlation, if you were to plot that function, you would see that it's sort of like this funky wrapped around thing. So the next step is just to kind of unwrap that. And then you should be able to plot your cross correlation function and look at it. I added an extra step here to normalize it, because that can help sometimes if you're trying to fit the peak of your cross correlation. But again, it's kind of not always necessary. So in the end, this is what your cross correlation function should look like. What you'll see here on BJ's screen is it's kind of it's flipped compared to the plot from Sharon earlier, but it's essentially the same thing. You're just thinking about it in different ways. And so the peak or centroid of this, I guess it's better to think of centroid, because sometimes you can have an asymmetric cross correlation function, in which case the centroid may not match up with the peak. But your center of light here is going to give you your Doppler shift, or your velocity shift that you have between these two spectra. And so that's what we're interested in. We're interested in finding the centroid of that, and then that's how we measure our radial velocity. And we know the shift between the two spectra.
All right, thank you. Okay, so we have this notebook up, and there's a couple activities down at the bottom. So the first one, notice that Heather didn't tell you exactly how we locate the center of this peak. So that's one of the activities for you. So I encourage everyone to try to get this notebook up and running on their machine, play with it, try to understand what's going on with the cross correlation, and then tackle these activities while we're here to help with any issues. So try to find a method to locate the peak of this function precisely. And then, as I mentioned before, back up here, we actually loaded a series of spectra. So the second part of the activity is to basically loop over all those spectra, calculate the velocity for all of them, and plot the time series or velocity as a function of spectrum index would be fine. You don't have actually time. So you can see how it changes with respect to each one of these spectra. All right, so we're going to be monitoring the Q&A on Zoom and the hands-on Slack channel for questions. There is only, what, 3 of us or 4 of us online, and there's a lot of you. So For any of those that are more advanced or that may have already gone through these notebooks, please help us out by answering others' questions as well, at least on the Slack channel as you can. All right, so.
Yeah, I think that's exactly right, BJ. That's a very good point to help out and answer things. The other thing I want to remind everyone, if you are getting stuck and you're having a problem and you can't get your Jupyter notebooks working or something, that doesn't exclude you from the Planet Hunt Challenge, because you can still use the DACE online GUI to go ahead and fit those Keplerians like Nathan and I walked you through yesterday. So if you are having too many difficulties or the programming is a little bit past your expertise at this stage, don't worry, because you can still continue to the next stage. But if you are able to go through the Jupyter Notebook, then this should hopefully give you a really good idea of the guts of what a radial velocity measurement is and how you derive those.
Another thing I'll say is that the complicated packages that we've been having trouble install, spleef and Kepderiv should not be needed for this notebook. So if you can't get that working, just push forward and we'll deal with that tomorrow or later.
Yeah, absolutely.
But you should be able to run this notebook.
There was a question in Slack saying, I was wondering why this CCF peak seems less broadened than the CCFs we see in Sharon's talk.
Yeah, I'm already on it, at least. Although if someone wants to answer live, by all means.
That's fine. You can answer there.
So one question that I've noticed that's in the Q&A is, how can we accurately compensate for the asymmetry with respect to the centroid of the CCF? So I'm not going to directly answer that, because I'm going to leave that to sort of that bonus activity for you to think about with that, and we can kind of come back to it. And it's something I might touch on my talk briefly, and perhaps some of the others talking about stellar variability tomorrow. But one thing to keep in mind is, if you have an asymmetry and that asymmetry is constant, then you will have injected just a systematic shift. And as Jason reminded us earlier and pointed out, as exoplanet hunters, we're interested in the relative shifts. So if it's just an absolute shift that isn't time variable, then it's not going to be too much of a problem. Your problem gets into if you have time varying asymmetries, which then is a whole nother bag, and we'll talk a little bit more on that on Wednesday. And if you have ideas about fitting, taking into account the asymmetries, that's a whole realm of research. So go ahead and delve into it.
So we're going to allow the attendees to unmute in case it's easier for you guys to ask questions verbally rather than type everything out. So we'll see how this goes. If there's a lot of people trying to speak at once, it may not work, but try it out.
This is Swastik. So I have a question. When you are measuring radial velocity for, my question is that how do you understand, like, what are the typical radial velocities that you get for, let's say it's a planet or it's some other celestial object? Is it possible, like my question is, how do you differentiate from radial velocity that an object is a planet or some other stellar objects? Is it possible to differentiate?
Yeah, so the difference between a planet and a star, for example, is usually about an order of magnitude in the amplitude. So a star orbiting another star will produce a rate of velocity shift of order kilometers per second, whereas planets are going to be an order of magnitude less, of order meters per second. That's not always the case because of that M sin I issue, but generally that's the way it works. There's more complicated issues, though, when you're trying to determine whether it's a planet or just some source of stellar variability from the star, the surface of the star moving, because those can be on basically the same amplitudes. You're looking at meter per second amplitudes. And especially when you're looking at really small planet detections that have sub-meter per second amplitudes, it's easy to confuse that with stellar activity. So for that, it's usually best to look at other indicators that track stellar variability. You can look at photometry, you can look at various spectral lines, look at the shapes of the spectral lines. This is a very active area of research, and there's a lot of ideas on to how to tackle this big problem to detect small planets.
To add to that, there's usually kind of a mass cutoff. So in some of the earlier talks, and in particular Jason's, there was how you convert the amplitude of the Doppler shift to a physical mass. And if you have a mass above 13 Jupiter masses, that's sometimes considered then to be a brown dwarf, or sort of a failed or small star. So getting onto that it can be a debate in its own right. What is a brown dwarf versus what is a gaseous planet? But that is kind of one thing to keep in mind as we look at what does the mass tell us. But then, of course, as BJ said, sometimes you can think that you're detecting a planet and you have a mass of blah, but really it's a spurious signal coming from something else, usually the star itself. And we'll talk about that tomorrow.
Hey guys, I've been unmuted, so I guess I'm up. But first of all, just thanks a lot for doing this. This is really awesome. And my question is about this Jupyter notebook here. It seems like we have a series of spectra, and the first one was chosen to be a model, sort of like a mask that we were speaking of before. Was that sort of just an arbitrary decision for the sake of a pedagogical exercise, or is there some reason that specific spectrum was chosen to be our model here?
Yeah, no, that's totally arbitrary. You can choose any of the spectra as your reference. So if you go back to here, I'll share again this little diagram from Sharon Wang. We have the model or the reference in blue here, and then the observed spectrum in black. In the case in the notebook here, the model or reference is just any one of the spectrum that's in our series. And so we're cross-correlating that against the other ones. And what you're going to measure is the relative shift between your reference and your target, right? So there may be a gamma offset, a overall rate of velocity shift that's different depending on which reference spectrum you choose. But again, that's not really important for planet hunting. We only care about relative rate of velocity shifts.
Got it, thanks.
Yeah, and to add to that, just a note that what Sharon was showing there is a set of delta functions, and that's commonly used. For example, the HARPS pipeline, HARPS North pipeline, Espresso, they all use a mask that is just binary, just delta functions like that. And they're often weighted towards lines that are deeper have a stronger weight because you can get better precision from those. So just some of the subtleties that you might see. And there are some advantages of choosing a binary versus a stellar template, but it can be quite tricky. For example, for M dwarfs, if I remember correctly, you often can get more precise radial velocities if you use like an actual observed spectra rather than to try to use a set of delta functions.
Yes, for M dwarfs that have very rich spectra, it's more straightforward and to use the stellar spectrum. So you just take all the spectra, you shift them to a common velocity, and then you take the average and use that as the cross-correlation template. That also works for solar-type stars. I think certainly at the meter per second level, it can be shown that both approaches give the same results, basically. Pushing to 10 centimeters per second, I don't know whether there are subtle differences, but certainly if your spectrum is very, very rich in information, doing a synthetic mask is quite difficult, and using a stellar spectrum as a template is more straightforward.
Yeah, I mean, one of the underlying assumptions that is commonly used with the mask is that it doesn't work all that well when you've got blended lines, which is a problem in M dwarf spectra because all the lines are blended. So if you have a G-star spectrum, then you can come up with a set of lines that are reasonably separated, and that works well with a binary mask. But things get more complicated once they start to blend together.
So to clarify, I don't want to hog up the space here, but it's awfully quiet. So I'm just going to ask, for the activity, the second activity here is to measure the RV for each spectrum in the series. I'm assuming using your method from number 1, right, to find the peak, but it is, I guess, to calculate the actual RV signal due to a companion, wouldn't you need some sort of offset here? Or are we just, for the sake of this activity, just talking about basically just find the peak, find the sort of net overall radial velocity?
Yeah, for the sake of this activity, we're just finding the radial velocities and plotting that as a function of spectrum index. You don't even have timestamps here to really properly do a planet finding. This is just kind of a warm-up to get you an understanding of how the radial velocities that you're going to be given for the Planet Hunt Challenge are calculated to some extent.
Yeah,
Okay,
so the way to think about it is that each one of those spectra was taken at a different moment in time. So it's just you just don't have the timestamp to go with it. You would just use the index, I guess.
Great, thank you.
Yep, so you should be able to see different velocity shifts amongst them.
Is there any upper limit on V Sine on which you can detect the planets? Is there any cutoff limit, like up to what V Sine can you use radial velocity technique to detect planets?
Yeah, definitely. It's not a hard limit. It's just that as you get to higher rotational velocities, higher V Sine I, it becomes more and more difficult to extract radial velocities precisely. So you lose precision. What's interesting, and so in stellar physics, there's this place called the Kraft break, which happens for stars that are hotter than a certain temperature. I think it's about 6250 Kelvin. Above that, stars tend to be rotating very quickly. And so it's kind of a hard break at that boundary. Stars hotter than that are really going to be difficult to measure radial velocities, both for the fact that they have higher V Sine I as soon as you get across that boundary. They also have a lot fewer spectral lines. Cooler stars tend to have more spectral lines, and that gives you more information to measure the radial velocity.
So I'll offer a minor caveat. Precise RVs can be used on hotter stars that are not rapidly rotating. There are lots of subdwarfs and magnetic B stars. And one of the reasons hotter stars have fewer lines is the broadening just washes them out. But slowly rotating B stars can actually have a lot of lines, and some of them pulsate. And so precise RVs can be used to study pulsations and look for companions around slowly rotating hot stars. And there's been a little bit of work on that. And you can get down to giant planet masses generally.
So I guess I'm unmuted. Can you hear me?
Yep.
So you said that the edges of our slices of the spectra are being padded with zeros. It seems like that would look like an absorption feature, right? Like an absorption line on some level. So how are we avoiding edge effects, giving us systematic results here and calculating the peak of our CCF?
Yeah, there should be a note in there about you want to zero pad your vectors to length of 2n minus 1, where n is the length of your vector. So that's like you have a lot of zeros. So that's why it's not going to be, it shouldn't be appearing as an edge effect.
Is there not a point where like you're going from some value to suddenly having like a step function where you're just going down to 0 at the edges? I mean, it seems like a sudden...
I think you will, yes. It will have an effect on the CCF if you introduce an artificial edge.
But yeah, it's just outside the range of that you're analyzing in the CCF.
Okay.
Yeah, because what we're looking for often is sub-pixel shifts. And so you will usually have zero padded far beyond that.
Yeah. Okay.
Wait, we're padding in wavelength space, right? Not in shift space.
Yeah.
Okay.
Yeah, that's true.
Yeah, good point.
Yeah, I think it will have a small effect, but most of the information that contains the Doppler shift is in the spectrum. So it will bias things a little bit towards zero shift.
Okay, but we have enough lines here anyway that that's not too much of a deal, I guess.
Yeah.
Thank you.
Jason, there's a question in the Q&A that I think I almost typed in an answer for. but I suspect you can give a more complete answer, which is ultimately how efficient is radial velocity in finding planets? Yeah.
Ultimately, it depends on the planets. So I'd say at the precisions we typically have, if what you're looking for are giant planets within 10 AU around well-behaved single stars, you can basically find all of them, but there's all sorts of caveats in there. If it's too active or young, you will get confused by stellar magnetic activity. And there's lots of if it's a giant star, for instance, there's both a lot of jitter and it's typically quite massive. So I think for the typical sort of, solar type, GK, old single bright stars, RVs, we'll find most of the giant planets. And if you have enough RVs and you work really hard, you can get down to the sub-Neptunes and stuff. BJ has a nice paper with Andrew Howard about the detection limits of the Keck high-res sample after 2 decades of observations at sort of 1 to 2 meter a second precision with hundreds of observations per star. And so as baselines increase and RV precision improves, that'll get better. Maybe I think that's what you're.
Well, I think that answers it. But there was another aspect of this that I was kind of you touched on it in your talk and a couple of times in your answer, but circuitously, which is that the period is nonlinear. And so if you're thinking about this from a telescope efficiency standpoint and how much observing time you need, then I think your answer maybe changes a little bit. Or is tempered by by that initial problem.
Wait, I'm sorry, which period thing are you thinking of? Long period?
The orbital period is a very nonlinear parameter. And so it can be if you know the orbital period, then RVs are very efficient at digging out planet signals. But if you're starting from 0.
For sure. Okay, so right. So if you just want to know, do any planets exist, then you have to sample all the periods that they could be at to disambiguate that. And so you're talking about dozens of periods for high amplitude planets. And for lower amplitude planets closer to your noise, you're talking about hundreds of observations to really get them all cleaned out, or maybe 100 observations. But that's right, if you're talking about a transiting planet and you know what you're looking for exactly, and you're willing to accept that a one planet model, then in principle, it just depends on your precision and when you can look at quadrature. You can have an optimal observing scheme to just measure the mass of that one planet. The problem is they usually have friends, and usually have to characterize the friends to get that one planet, which means you're back to doing lots of observations anyway.
So the point is, it's a very complicated question, and RV is never efficient, but it is very powerful.
Hi everyone. So I have another question. So in the coming decades, we can see that there are planets that are detected by direct imaging. So those planets are actually far away from their host stars usually. So my question is that using radial velocity in near future or maybe in the next decade, is it possible to use the same technique to detect any exomoons or something like that? Is it possible technically?
I don't think so. I mean, I'm not going to say it's impossible. It's a very different problem, though. Those giant planets are typically rapidly rotating. They're quite faint, and they're only observed at mid or near infrared wavelengths. So your photon starved, you're typically doing this. You also need your spectrograph to be behind a coronagraph to detect them. And typically we don't put high resolution spectrograph feeds behind coronagraphs. So while it's not impossible, in general, I don't think it's possible with any instruments people are thinking about today, but maybe I'm unaware of one. Their rapid rotations will also make it hard to do any kind of really precise RVs. On the other hand, the mass ratios aren't that far off, so maybe you don't need meter a second precision.
Yeah, for looking for exomoons, the best chance is probably transits, because if you have a very large exomoon, it would be visible if it transits the star as a dip close to the transit of the parent planet. Also, as the moon is orbiting the planet, the transit time would shift somewhat. So those are observable effects that one can reasonably look for, and there are groups that actually do that in transit data. In radial velocities, it's much more difficult, and as you say, in spectroscopy, it's also much more difficult to look for moons.
For the directly imaged planets, though, they'll be quite young for the most part, and so they may still have proto-lunar disks. And there's a lot of work using ALMA and other instruments to try and detect those as well.
Hi, I have a question. Is there any upcoming facility that is planned to do radial velocity follow-up of planets that may be discovered with Gaia astrometry, that it will be devoted to that? Because I guess that astrometry planets will have long periods, and to do a radial velocity follow-up would be expensive to do. So is there any upcoming facility that is going to be devoted only to do that? Because there may be many. So.
I'm not aware of one. A challenge there is that those stars will typically be quite faint, and the period drop-off of amplitude isn't very strong, but it'll take a lot of telescope time to follow those up with RVs. I suspect if there are some that are particularly interesting, that people will pursue them with existing facilities, like the Keck Planet Finder or Espresso. I think in general, it'll go the other way, that Gaia will measure the full astrometric solution of known RV planets that already have 20 years of measurements.
Yes, and there's certainly a hope that we can stitch together information from Gaia and RV on different planets in the same system. So if we are lucky, we may know the inner planets from RV and find outer planets from Gaia. And of course, that is very, very valuable information.
I'll also just add that since the planet orbital periods are quite long, you don't necessarily need to track the orbit throughout the entire time. You can get a point every month. You don't need to get it every single night for an orbital period that's 10 years long, say. So you don't actually need to track it for the whole time. It's not as much telescope time as you might think.
So there are a few more questions in the Q&A, I think, or one at least.
Yeah, so we have one. Is gravitational lensing taken into account in the process of studying the star for finding the exoplanet? If yes, can someone describe briefly about it? So gravitational lensing is used as an entirely separate technique to detect exoplanets. It's called microlensing. But in radial velocity technique, gravitational lensing is not something that we have to worry about. Yeah, is there anything else that anyone wants to add?
No, that's right. Even during a transit, it's a negligible effect.
Yeah. Okay. And then have higher point correlations been studied, say, to look at signatures of non-Gaussianity, like 3-point functions? I'm not exactly sure how to answer this. Anyone else?
I'm not quite sure what it's asking.
Yeah, I'm not sure.
Yeah, so I don't think I can make a statement about whether or not this has been studied, but I think that more to the point is that we're limited by much simpler terms, I think, in measuring RVs, and many of them Heather and other folks are going to talk about tomorrow in stellar activity. But even fundamental issues in line positions in the photosphere, there's been a lot of work over the last half a decade by the folks in Geneva starting to do line by line analyses. And so I think there's much lower hanging fruit. We're not nearly as sophisticated as you might imagine we are.
Yeah, I agree with that.
That's the best I can do for that one.
Okay, we got a couple new ones that came in. So concerning the gamma term, if we are observing the same star with different instruments, is the offset between RV sets coming almost entirely from the instrument? I would say usually yes. The stellar contribution is quite unpredictable and hard to derive, right? Yes, generally. And so generally when you're fitting radial velocity curves from multiple instruments, you simply assign different gammas to each instrument and fit them as part of your Keplerian model. This is simply a nuisance parameter that you have to deal with. So sometimes radial velocities can be reported in terms of an absolute velocity, especially for instruments that use the cross correlation technique. You'll see that the mean velocity is something like, you know, negative 19,000 meters per second or something, where other data sets you'll be given will just have a mean around 0. And those differences don't really mean anything. It has to do with the instrument and the reduction pipeline. So that's why you're always going to want to fit for these gammas.
And by the way, in days, when you use days for the RV challenge, you'll see that by default, the offsets of the instruments are always fitted. They are always included in the calculation of the periodogram of any kind of fit. It's always refitted. And sometimes you have an idea of the difference between two instruments. So you don't necessarily know the absolute value of the offset, but you know that one instrument is somewhere and compared to another, and you can put a prior on this. And this might be useful, especially if you have one instrument very far in the past and far in the future, and the other far in the future.
The practical effect of that is that if you're tracking a long period planet, you can't switch instruments because you can't tell the difference between something that happened in between and just an instrument offset. In principle, you could try and determine what the offset is between instruments. And that might be possible between two closely related instruments. For instance, when Keck high-res was updated, they didn't change the iodine cell. And so there's a small offset between, but we have a sense of how big it is. But in general, it's safest just to treat them as independent. So if you want to find a period of 20 years, you got to have you have to have something that's stable for 20 years to track it.
I would add one caveat to that, which I think is only recently becoming available. Now that we are starting to have spectrographs with laser frequency combs, which are calibrated in an absolute sense to the SI NIST second, in principle, we should be able to back out the offsets from two different laser frequency comb instruments in two different locations, if you can track that exactly. It's complicated, but it's an advance that we haven't had in the past, because when we've been tied to lamps, we're tied to two different lamps that have slightly different fill gases, and they're all different pressures, and they're operated at different temperatures. So every lamp, you know, the underlying atomic lines are all the same, but they're shifted slightly within the lamp or even over time as the lamps age. Now we actually, as we're moving to these frequency combs, we have a fundamental reference that is dramatically many orders of magnitude more precise than anything that we care about for RVs.
But still, there's a caveat at the precision that we are interested in. One cannot assume that this difference between instruments is the same for each star. Yes. So I don't think really at that precision that you can determine an instrument offset. You have to do it on a star-by-star basis and essentially fit for it, because it's not just the instrumental shift and the calibration of the instrument, it's also the sampling that is different. And so with different detectors, you always cross-correlate something that is slightly different, also due to other effects that are not just the stability of the calibration. There are other things entering. And so you may have, if you compare two instruments, there may be a constant between them that is large, but then from star to star, you have some variations of this constant that may still be several meters per second.
Yeah. That brings up a good point, which is Jason's referred to the offset a couple of times as a nuisance parameter, which effectively it is. You have to think about what is the science that you want. You know, we may be able to measure very well absolute offsets between two instruments, but what is that bias? if we can throw a nuisance parameter in and fit for it, because it doesn't actually have any physics that we care about behind it. It certainly has physics behind it, mechanical engineering and material physics and whatnot, but I probably don't actually care about that. So, you know, you have to think about what you want and perhaps not overcomplicate the situation by trying to do it in an absolute sense if you can get away with a relative measurement.
Yeah, it might be nice if you could do it, because then you could actually put together data that were taken 20 years ago with one instrument, with data taken today with a different instrument, and look for really long period planets. But that may be possible on the level of a few tens of meters per second or something of that order, but probably it will not work on the 1 or a few meter per second level, because then these star-to-star variations come in. Each stellar spectrum looks a little bit differently, and therefore the difference between the instruments also looks slightly differently.
Andreas, while we have you, there's a question that I've seen a couple of times on the chat over the last couple of days that I would like you to answer. So it basically gets down to what are the giant telescopes going to be able to do for RV planet searches and helping us there? What are the complications in using a 30-meter class telescope to drive an RV spectrograph?
Yeah, the biggest complication is getting enough time on the telescope, because there are cosmologists in this world who would also like to get a lot of time on these telescopes, and other people doing interesting stellar astrophysics, for instance. So that is one big limitation of using a really big telescope, is the availability of time. In principle, of course, a big telescope is nice because it gives you a higher signal-to-noise ratio. I had the signal-to-noise ratio in my formulas yesterday, and so you need to collect a large number of photons if you want high precision. And if you have a big telescope, you can do that for a fainter star, or you can do that more quickly for any given star. Typically, I think in this field, the telescopes that are just a little bit smaller than the biggest telescope available at any time have, by and large, have a large impact, because you can get a lot more time on these slightly smaller telescopes than on the big telescopes. And that offsets the advantages of the big collecting area. So the big telescopes probably will have the biggest impact in some special projects in which, for instance, you find a really, really interesting planet by the transit method for which you desperately want to get the mass, and it is so faint that you really need the big collecting area, or some other special projects that you can do with somewhat more limited observing time.
It's also worth pointing out that it's very difficult to build spectrographs for these giant telescopes because of A-omega, A-Tundu issues. You have to compromise somewhere or have a giant bank account. The G-clef spectrograph for the GMT is lower resolution than many of the other spectrographs that are being built for smaller telescopes, because you just can't get a grating that is big enough, and so, you know, something has to give. Yeah, so as I explained yesterday, there's this trick of slicing, and by doing slicing not into 2 but into a much larger number of slices, you can build spectrographs for those telescopes at high resolution. It's being done also for other reasons, because, for instance, you want to do absorption spectroscopy of extrasolar planets. So the transit spectroscopy method, that will really benefit from these large apertures, and you will be able to get atmospheric transmission spectra with much higher signal to noise, and for planets that are smaller than is currently possible. And in principle, so those instruments may be available, but as I say, probably with limited time available for radial velocities, because that is very time consuming to do. Oh, I wanted to also answer a question that I know I have seen maybe 5 times on the chat, on the Q&A, and that is the question about why most
systems are actually close to edge on. That was mentioned by several people. And so the answer to that is yes. Planetary systems have random orientations, so they are not aligned with a galactic disk or anything. The orientations are random, but that is random in 2 dimensions. And the best way I normally think about this, the most intuitive way, is to think that the orientation of the rotation axis, so the polar direction, that is random on a sphere. Or you can think about it about the orientation of the angular momentum vector. So the random orientation on the sphere means that it's much more likely to be orthogonal to our line of sight than to be along the line of sight. Along the line of sight is the polar axis or the rotation axis being close to our line of sight. Is like looking for real estate close to the pole, whereas being orthogonal to our line of sight is looking for real estate close to the equator. And there's just much more real estate, say, within a geographical latitude of 0 and 1 degree than there is between 89 degrees and 90 degrees. Mathematically speaking, what is equally distributed is not the inclination angle, it's the cosine of the inclination angle. And that means that most systems are really close to edge on, and the numbers for that are in my pre-recorded talk.
So there's a question that I've seen a couple times there about binary stars. How is a binary star and planet system disentangled? So basically, it's very difficult. The main problem is when you're observing a binary star system with radial velocities, you have 2 sets of lines that you have to deal with. So your cross-correlation function becomes double peaked, and those peaks are always moving relative to each other, and you have to find a small perturbation of one of those peaks or both of those peaks on top of that. So it becomes very difficult. It's possible in theory, but there's not been a lot of work on this. So yeah, it's a research project to be done. So we are over the allotted time, so feel free to log off. I will again be sticking around for the rest of the afternoon on Slack to help answer any questions. I plan to post a sort of answer key version of this notebook within the next couple days before the end of the week. So you can see what I've done for the activities, but there's not one right answer for any of these. It's definitely open-ended. I can stick around for a bit and try to tackle some of these remaining questions.
Okay, yeah, it's totally up to you.
They're still on. Okay, how do we calculate V sine I for binary stars and planet systems? Also, can we calculate how many planets are revolving a star by calculating its wobble? So V sine I is generally calculated by looking at the spectrum, and the width of the lines is dependent on V sine I. So if it's a higher V sine I star, if it's rotating more quickly, you're going to have very broad spectral lines. And so you can use that to measure V sine I. And yeah, we can calculate how many planets are revolving a star. Basically, using the periodogram technique is one way to do it. Basically, you have to disentangle all of the individual Keplerian orbits in some way. So you can use periodograms, you can use GPs. There's a variety of different ways to try to figure out how many signals are within your radial velocity data set. Is any extragalactic planet ever possible to be detected by radial velocity technique in the next 30 years, maybe? It's a good question. Perhaps very massive exoplanets, but probably not. The main limitation is that for this technique, you need a lot of photons. And so when you're looking at stars in other galaxies, you're generally struggling to collect enough photons to get enough signal to make these precision radial velocity measurements. So maybe with 30-meter telescopes of the future or larger telescopes, it would be possible to collect enough of those photons to get precisions that allow you to detect sort of super Jupiter mass planets. But there's other techniques like microlensing, which are probably going to be better to detect exoplanets in other galaxies before then.
Hi, BJ, and so I have a question. So in the planetary mass and orbital period parameter space, if you see, so mostly the large orbital period and low mass planets, that space is quite empty. So mostly by direct imaging, we have high mass planets and the higher orbital period. So in the near future, which method or what do you think, how will we probe that region of the space? What is your thought on that to both of you, my question?
Yeah, so pushing to longer period orbits and lower mass planets is kind of the goal of most exoplanet hunting techniques. I think in the near future, the most promising, to some extent, is going to be the Gaia mission with astrometry. We're going to get some down to about Jupiter mass planets, but farther out. We also have long duration rate velocity campaigns that are going to be good for the slightly higher mass planets as well, kind of in that same regime, but pushing out to maybe 10 to 30 AU. We have rate of velocity campaigns that have been going since 1990, so we're starting to get to pretty long orbital periods now. And then there's the Roman Space Telescope, which is going to use microlensing to detect a whole bunch of planets. I think that's going to be probably the best near-term mission to really push down into that region of small planets at long orbital periods. The problem there is that we're only going to get statistics about those planets. We're not going to be able to follow up individual planets, because once you detect a microlensing event, that's it. That's all you have. You can't go back and reobserve it. So yeah, I hope that helps to answer your question a bit. Okay, so here's another question. Do radial velocity measurements, can they help probe into planet formation scenarios? Yeah, I think basically anything that helps you understand the population of planets that exist can to help understand or infer at least what's going on with planet formation. It's difficult to directly measure anything going on with planet formation using the rate of velocity technique, because young stars are typically very active in rate of velocities. They have a lot of noise, and so it's difficult to detect planets around very young stars as they're just forming. But you can infer what happened with planet formation based on the population of planets that you observe.
Another way that they're really useful for that, I mean, population is, I think, the right answer, but radial velocities are very good at giving you the full set of orbital parameters for a planet. And once you start building up populations of orbital parameters, then those feed directly back into planet formation models. There's a whole series of papers over the last 3 or 4 years by Caitlin Crater and Max Moe looking into this. The fast rotators question, which has come up a few times, is difficult. So if you do a Bushi information content, Q content calculation, those spectra have lower information content, which means it's because the lines are so broad. So it's hard to measure precise radial velocities. The information content feeds directly back into the fundamental precision that you can get. And so one of the problems with that, this has come up a couple of times in some of the follow-up conversations, is we have a limited amount of telescope time and a limited number of RV spectrographs. And so you choose typically the stars to go after where you can get the most promising planet signals, which is not the right answer if you want a unbiased set of observations. But RV surveys have always had many observational biases at their most fundamental level, and so we tend to target things that are both scientifically important and also have a hope of actually measuring a planet signal if there's a planet there. And so that's, for those reasons, the rapid rotators, where it's not clear that we could measure a planet signal even if it is there, typically get rejected very early on in surveys.
All right, I think I'll take this last question, and then probably sign off. We're going to cut these off at some point, but I thank the attendees for all the great questions. This is definitely a good conversation. So assuming we're able to detect planets in another galaxy, do we still just need to do the regular corrections, for instance, barycentric, or somehow should we need to take into account the sun's velocity through the galaxy, and what about the star's velocity in its host galaxy? So in theory, you might want to make corrections for all of those things, but in practice, you only really need to worry about things that vary on timescales that are similar to your orbital period of your planet. So the velocity of the sun through the galaxy is not changing quickly enough that you're going to have to worry about it. And similarly for the star in the other galaxy, assuming it's not too close to the center, those things are going to be a small, they're going to change very small relative to the timescale of a planet's orbit. So you can essentially include that as a gamma term. It's just a nuisance parameter that you're not going to have to worry about in terms of exoplanet detection.
And I think with that, I've got to sign off, but I will still be monitoring the Slack channel throughout the afternoon here on the West Coast.
Yeah, as will I. So
by all means, post questions or problems that you're having there, and we will try to troubleshoot them.